The universe has at least 12 completely different origin stories, and most of them will break your brain. From quantum fluctuations creating everything from nothing, to our entire reality being the inside of a black hole, to the possibility that none of this is even real. Today, I'm breaking down every major theory of how the universe began, starting with the one we're most sure about, the Big Bang Theory. Most people picture the Big Bang wrong. They imagine a massive explosion detonating in the middle of empty space, like a cosmic bomb going off in a dark room. That's not what happened, not even close. The Big Bang wasn't an explosion into space, it was an expansion of space itself. There was no dark room, there was no outside. There wasn't even a before in any meaningful sense, because time itself began with the expansion. In 1927, Georges Lemaître proposed that the universe was expanding from an incredibly dense state. 2 years later, Edwin Hubble confirmed it. Every galaxy he observed was moving away from us, and the farther away it was, the faster it receded. The universe had a direction, it had a history. And that history starts roughly 13.8 billion years ago, when everything existed in a state so hot that temperatures exceeded 1 trillion Kelvin. The sun's surface? About 5,800 Kelvin. But the real smoking gun came in 1964. Two radio astronomers detected a faint microwave signal coming from every direction in the sky. The cosmic microwave background radiation, leftover heat from the early universe, still faintly glowing 13.8 billion years later. They literally heard the echo of creation. Here's the thing, the Big Bang isn't just popular. It's the only origin theory supported by three independent lines of evidence: galaxy redshift, CMB measurements, and the observed abundance of light elements like hydrogen and helium. Every other theory you're about to hear either builds on it, tries to fix it, or throws it out entirely. But the Big Bang has a problem, a big one, and it took a physicist named Alan Guth to figure out what was missing. Cosmic inflation. The Big Bang has a problem. Actually, it has two massive problems, and without solving them, the entire model falls apart. Here's the first one. Look in any direction in the sky. The temperature of the leftover radiation from the Big Bang is almost exactly the same everywhere. Sounds fine, right? Except those regions of space are so far apart they never could have been in contact with each other. They never had time to exchange heat, share energy, or equalize. So why do they look identical? That's the horizon problem, and the standard Big Bang has zero explanation for it. Problem 2, the geometry of the universe is flat. Not curved, not warped. Perfectly, suspiciously flat. For that to be the case, the energy density of the early universe had to be fine-tuned to an almost impossible degree. That's the flatness problem. In 1980, a physicist named Alan Guth proposed a fix for both. He called it cosmic inflation. The idea is simple, but the scale is absolutely insane. Roughly 10 to the negative 36 seconds after the Big Bang, the universe started expanding exponentially. Not gradually, exponentially. And this entire expansion lasted until about 10 to the negative 32 seconds. In that window, something smaller than a subatomic particle inflated to something potentially much larger than the observable universe today. Every explosion you've ever seen is a hiccup compared to this. But here's the thing, inflation didn't just solve those two problems, it accidentally explained why galaxies exist. During inflation, tiny quantum fluctuations, basically random noise at the subatomic level, got stretched to cosmic scales. Those fluctuations became the seeds of every galaxy, every cluster, every void in the universe. The structure of everything you see in the night sky started as quantum static. And this isn't just elegant math. Planck satellite data from 2013 and 2018 confirmed specific patterns in the cosmic microwave background that inflation predicted decades earlier. The predictions matched. The debate now isn't whether inflation's math works. It's whether the theory is truly falsifiable, whether it can ever be proven wrong, or whether it's so flexible it can explain anything. That's an active, unresolved fight in physics right now. But at least inflation tries to play by the rules of evidence. The next theory on our list, it threw out the Big Bang entirely and said the universe never had a beginning at all. Steady state theory. In 1948, three physicists decided the universe didn't need a beginning. Fred Hoyle, Thomas Gold, and Hermann Banda proposed something radical. The universe has always existed, always looked roughly the same, and will continue looking the same forever. No dramatic birth, no cosmic explosion. just an infinite, eternal cosmos quietly creating new matter to fill the gaps as space expands. About one hydrogen atom per cubic meter per 100 billion years. Barely anything, but enough to keep the universe looking unchanged for eternity. And here's the thing, this wasn't just a scientific theory, it was personal. Hoyle found the idea of a cosmic beginning philosophically unacceptable. The notion that everything erupted from some impossibly hot, dense state felt too convenient, too close to a creation myth wearing a lab coat. So he built a model that didn't need one. A universe with no first page, no let there be light, just existence, stretching backward and forward forever. But Hoyle's biggest contribution to cosmology wasn't his own theory. It was naming his enemies. In 1949, during a BBC radio interview, Hoyle dismissed the competing theory by calling it a Big Bang. He meant it as mockery, a way to make the idea sound ridiculous and childish. Instead, the name stuck. It became the single most recognized phrase in all of cosmology. The man who hated the theory gave it the best branding in scientific history. Then came 1964. Arno Penzias and Robert Wilson detected a faint hum of radiation coming from every direction in the sky. The cosmic microwave background, leftover heat from a young, hot, dense universe. Exactly the kind of universe Hoyle spent his career arguing never existed. The radiation from the very beginning he refused to believe in was what killed his theory. Hoyle never fully accepted it. He spent decades pushing modified versions, but the scientific community had moved on. A brilliant man, genuinely one of the great minds of 20th century astrophysics, undone by the one thing science punishes most, deciding your answer before asking the question. But if a universe with no beginning sounds strange, wait until you hear about one that never stops ending. The oscillating universe. Like the steady state model, this theory refuses to accept a single absolute beginning. But where steady state kept the universe frozen in eternal sameness, the oscillating universe puts it on a loop, a violent, dramatic, infinitely repeating loop. Richard Tolman explored the idea back in the 1930s, and John Barrow and Frank Tipler brought it back to life in 1986. The concept is deceptively simple. The universe doesn't just expand once. It expands, slows down, reverses, collapses back into an incomprehensibly dense point in what's called a big crunch, and then bounces. Another Big Bang, another universe, another cycle, infinitely. And here's the part that'll keep you up at night. Each cycle potentially resets the physical constants and initial conditions differently. That means every iteration of the universe could have slightly different laws of physics. Gravity a little stronger here, light a little slower there. Your life, every civilization that ever existed, playing out in an endless loop of variations, an eternal return with imperfections forever. But there's a catch, entropy. The second law of thermodynamics says disorder always increases. If that holds true across cycles, then each successive universe is born into progressively more chaos than the last. The clean slate isn't clean at all. It's dirtier every single time. Eventually, the cycles degrade into thermodynamic noise. The eternal loop has an expiration date baked into its own physics. And then 1998 happened. Astronomers discovered that the universe's expansion isn't slowing down, it's accelerating. Dark energy is pushing everything apart faster and faster, which means a future big crunch is extremely unlikely for our universe. The cosmos literally told us it won't bounce back. It dealt a serious blow to the standard oscillating model, turning one of the most philosophically beautiful ideas in cosmology into something the universe itself seems to reject. But what if the universe doesn't need to bounce? What if instead of repeating, it just splits? The multiverse theory. Now we need to talk about something important. Every theory we've covered so far has had evidence you can point to. Observations, measurements, data. The multiverse is where that starts to change. This is where established science begins wrestling with its own philosophical limits. And honestly, it's one of the most exciting places in all of cosmology. Here's the setup. If cosmic inflation is real, and we have strong evidence that it is, then it almost certainly didn't happen just once. In 1986, physicist Andrej Linde formalized a model showing that inflation, once started, keeps going. Different regions of space inflate at different times. each one spawning its own self-contained universe in a process called eternal inflation. Our Big Bang wasn't the Big Bang, it was a Big Bang, one of potentially infinite others. And it gets bigger than that. There are actually 4 recognized types of multiverse. Quantum many worlds universes, where every quantum event splits reality. Inflationary bubble universes, where eternal inflation keeps creating new cosmic pockets. String theory landscape universes, where different mathematical solutions produce different realities. And mathematical multiverses, where every consistent mathematical structure exists as a physical universe somewhere. They come from completely different theories, but they all arrive at the same conclusion. There's more than one. Here's where it gets genuinely dizzying. Each bubble universe in eternal inflation could have completely different values for fundamental constants, different electron charges, different gravitational strengths, potentially different numbers of spatial dimensions. Our universe's laws of physics aren't the laws. They're just the local settings. By 2020, roughly 50% of theoretical physicists accepted the multiverse as a serious scientific possibility. Not fringe, not science fiction, a legitimate framework that follows logically from theories we already trust. But here's the problem, and it's a big one. The multiverse may be fundamentally untestable. By definition, other universes are causally disconnected from ours. You can never observe them. You can never measure them. And many physicists argue that if something can never be observed, even in principle, it stops being science and becomes philosophy. That's a real objection, and nobody has solved it yet, but if the multiverse is correct, the implications are staggering. There exists a version of you that made the opposite call in every single decision you've ever faced, every job you didn't take, every relationship you walked away from, every coin flip that went the other way. An infinite parallel army of you, each one equally real, each one living out a life you almost had. And if that concept doesn't make you feel very, very small, the next theory will. Because what if the entire universe, all of it, started from literally nothing? Quantum fluctuation. Empty space isn't empty. This isn't a theory, it's not a guess. It's one of the most well-tested facts in all of physics. At the quantum level, even a perfect vacuum is seething with activity. Particle-antiparticle pairs constantly pop into existence and annihilate each other, appearing and vanishing in intervals so brief they seem impossible. This has been measured. This has been confirmed. The vacuum of space is alive. Now here's where it gets complicated. Some physicists looked at this behavior and asked a question that changes everything. What if the Big Bang itself was just one of these fluctuations? Not a divine spark, not a cosmic trigger, not some unexplainable first cause, but a random quantum event in a pre-existing vacuum that just happened to be large enough and energetic enough to become an entire universe. Lawrence Krauss brought this idea to mainstream attention in 2012, and the central claim is staggering. Quantum mechanics allows something to emerge from nothing, no external cause required, no creator necessary. And there's math to back it up. The zero-energy universe hypothesis suggests the total energy of our universe is precisely zero. Matter carries positive energy. Gravity carries negative energy. They cancel out perfectly. If that's true, then creating a universe costs nothing at all, literally nothing. The books balance to zero, which means the universe doesn't violate any conservation laws by existing. It's the ultimate free lunch. But here's the philosophical minefield that nobody has successfully navigated. Critics, including serious physicists and philosophers, point out something uncomfortable. A quantum vacuum is not nothing. It has structure. It has rules. It has quantum fields baked into its very nature. Calling it nothing is like calling an empty spreadsheet blank when it still has formulas running in every cell. The debate over what nothing actually means has not been resolved, and honestly, it might never be. Still, if this model holds, the implications are enormous, as the universe required no spark, no intention, no cause. Quantum mechanics guarantees that all possible fluctuations will eventually occur given enough time. Our entire existence might be the universe's way of winning a lottery that was always going to be won. But if you think a universe from nothing is hard to wrap your head around, wait until you hear about a Nobel Prize winner who thinks our universe is just the latest in an infinite chain of universes, each one born from the death of the last. Conformal cyclic cosmology. Roger Penrose is not your average physicist. The man won the 2020 Nobel Prize for proving that black holes are an inevitable consequence of general relativity. He's one of the most respected mathematical minds alive. And in 2006, he proposed something that made most of his colleagues deeply uncomfortable. His idea is called conformal cyclic cosmology, and it goes like this. The universe doesn't bounce. It doesn't collapse and restart. Instead, it ages. It expands forever. Every black hole eventually evaporates. Every particle drifts so far apart that nothing interacts with anything ever again. The universe becomes infinitely cold, infinitely empty, and infinitely stretched out. Here's where it gets weird. Penrose realized that this final state, a universe with no mass, no structure, no scale, is mathematically identical to the conditions of a new Big Bang. Not similar, identical. The trick is a property of conformal geometry where, once you remove all mass from the equation, the universe literally loses the ability to define size. An infinitely large empty void and an infinitely small hot point become the same thing. The death of one universe is the birth of the next. No transition needed. Each cycle is called an aeon, and we're living in one right now, with no way to know how many came before us. But Penrose didn't stop at theory. He claimed he had proof. In 2010, he and physicist Vahe Gurzadyan published a paper identifying concentric circles of anomalously low temperature variance in the cosmic microwave background, patterns that Penrose argued were signatures of supermassive black hole collisions from the previous aeon. Then in 2018, Penrose and collaborators went further, publishing a paper introducing what they called Hawking points, specific bright spots in the CMB that they claimed were the ghosts of individual black hole evaporations bleeding through the transition between aeons. By 2011, multiple independent teams had already analyzed the original circle claims and concluded they were statistical noise, random patterns that any sufficiently large dataset would produce. The evidence, as of now, remains disputed at best, and that's the tension with CCC. The man behind it is a Nobel laureate with unimpeachable mathematical credentials. The framework is genuinely elegant, but the observational evidence hasn't convinced the broader community, and most cosmologists still treat it as a beautiful minority position rather than established science. The deepest implication, though, is almost impossible to wrap your head around. In CCC, the infinite future and the infinite past are the same thing. Time doesn't begin. Time doesn't end. It just rolls forward through aeon after aeon, each one a complete universe that has zero knowledge of the ones before it. But if one man's elegant geometry feels speculative, wait until you hear about a framework that generates more possible universes than atoms in existence. String theory landscape. Everything we've covered so far treats the fundamental building blocks of reality as point particles, tiny, dimensionless dots bouncing around and interacting. String theory says that's wrong. It proposes that the true fundamental constituents of reality aren't points at all, but one-dimensional vibrating strings. Different vibration patterns produce different particles. The same way different vibrations on a guitar string produce different notes. One string, infinite possibilities. Sounds elegant, and it is. But here's the thing, to make the math actually work, string theory requires 10 or 11 spatial dimensions, not the 3 you can see and move through. 10 or 11. The extras are supposedly compactified, curled up at scales so impossibly small that no instrument we've ever built, or likely ever will build, can detect them. And that's just the starting point. The mathematical framework of string theory doesn't produce one solution. It produces roughly 10 to the power of 500 possible solutions. Each solution represents a completely different possible universe, with different physical laws, different constants, different particle types. To put that number in perspective, there are roughly 10 to the power of 80 atoms in the entire observable universe. The string theory landscape has more possible universes than our universe has atoms, by an incomprehensible margin. Your brain literally cannot process how large that gap is. In 2003, Susskind formally laid out this landscape, arguing that our universe simply occupies one solution in this impossibly vast space of possibilities. The constants we observe aren't fine-tuned by design. They're just the pocket we happen to inhabit. We don't live in a special universe. We live in one of 10 to the power of 500 options. And we're here because this particular option allows us to exist. Now, here's where it gets complicated. As of today, there is zero direct experimental evidence for extra dimensions, zero evidence for string theory itself. Roughly $1 billion is spent annually across institutions worldwide on string theory research, and there hasn't been a single confirmed experimental prediction since the framework emerged in the 1980s. That's not a fringe criticism. That's a genuine heated debate happening inside physics departments right now. And the core criticism is brutal. A theory that predicts 10 to the power of 500 possible universes effectively predicts everything. And a theory that predicts everything predicts nothing. If literally any outcome is consistent with your framework has zero explanatory power. It can't be wrong, which means it can't be tested, which means some physicists argue it isn't science at all. But if you think string theory's extra dimensions sound wild, wait until you hear about a model where our entire universe was created by two higher dimensional membranes slamming into each other. The ekpyrotic scenario. Everything we've covered so far assumes the Big Bang was some kind of beginning, a starting point, a moment where the universe flickered into existence from nothing, or from quantum foam, or from the collapse of a previous cycle. But in 2001, a team of physicists, including Justin Corey, Bert Overath, Paul Steinhardt, and Neil Turok, proposed something radically different. The Big Bang wasn't a beginning at all. It was a car crash. Here's the setup. String theory predicts that our universe exists on a three-dimensional membrane, a brain, floating in a higher dimensional space. And we're not alone in there. Another brain floats parallel to ours, separated by a gap smaller than an atomic nucleus. Two entire universes hovering next to each other, close enough to touch. And according to the ekpyrotic scenario, they did touch. The two brains drifted together over an incomprehensible timescale, made contact, and collided. The energy released from that impact produced everything: matter, radiation, the expansion of space itself. What we call the Big Bang was not creation, it was destruction. We are the wreckage of a cosmic collision between parallel universes, and the observable universe, every galaxy, every star, every atom in your body is the debris field. That's not poetry, that's literally the model. And here's what makes it interesting beyond the cinematic framing. The ekpyrotic model predicts a universe that is geometrically flat and infinite. That's exactly what we observe. It also avoids some of the mathematical infinities that plague inflationary models, the ones where equations blow up and physicists have to patch things together with workarounds. The collision framework sidesteps those problems entirely. It was designed specifically as a competitor to cosmic inflation, not a companion to it. A completely different explanation for why the universe looks the way it does. But the fundamental problem is brutal. The entire theory is built on string theory, which remains unconfirmed. It requires extra dimensions that nobody has ever detected. And worst of all, there is currently no observational tool that can distinguish the ekpyrotic model from standard inflation. Both predict the same flat, uniform universe. Both explain the same cosmic microwave background patterns. The math works beautifully. The evidence to separate it from its rival simply doesn't exist yet. It's a theory that solves real problems but inherits every piece of baggage string theory carries. And until someone figures out how to test it, that's exactly where it stays. But if the idea of our universe being born from a collision sounds extreme, wait until you hear the theory that says we were born inside something even more violent. Black hole genesis. In 1992, physicist Lee Smolin asked a question so deceptively simple it's almost embarrassing nobody asked it sooner. What if universes reproduce, not metaphorically, literally? Smolin proposed that our universe was born inside a black hole that exists in a parent universe, and every black hole our universe creates, each one births a brand new universe inside itself, an endless recursive chain of cosmoses giving birth to cosmoses. He called it cosmic natural selection. And yes, it works exactly like Darwin's evolution, but for reality itself. Here's how it plays out. Each child universe inherits the physical constants of its parent, but with slight mutations, tiny variations in the strength of gravity, the mass of an electron, the speed of light. Universes whose constants happen to produce lots of black holes create lots of offspring. Universes whose constants don't, dead ends, no children. Over billions of generations, physical constants naturally evolve toward values that maximize black hole production. And here's the thing, our universe is absurdly good at making black holes. Stellar mass black holes, supermassive black holes at the center of nearly every galaxy, potentially primordial black holes from the earliest moments of existence. Under Smolin's model, that's not a coincidence. That's a result of cosmological natural selection fine-tuning our universe across countless generations of parent universes before us. Now sit with this for a second. You, this planet, every star and galaxy in the observable universe, all of it may exist inside a black hole sitting in another universe, which is itself inside a black hole in a universe above that. Infinite nesting. Reality is a set of Russian dolls where every layer contains billions of doors to layers beneath it. But before you get too comfortable with how elegant this sounds, the theory has a massive hole of its own. The mechanism for how physical information crosses a black hole singularity, how constants get passed from parent to child, is completely unsolved. The math breaks down exactly at the point where the theory needs it most. The singularity is a wall, and Smolin's model requires something to pass through it. What it does have is a genuinely testable prediction. If cosmic natural selection is real, our universe's constants should cluster around values that maximize black hole formation. And observations are partially consistent with this, partially. The prediction isn't precise enough for a strong confirmation, but it's more than most theories on this list can offer. A universe that evolves, that reproduces, that optimizes itself across generations. It's genuinely one of the strangest ideas in cosmology, but if you think a universe born inside a black hole is weird, wait until you hear the theory that says none of this is real at all. Digital simulation theory. Yeah, we need to talk about The Matrix, not the movie, but the actual philosophical argument that inspired it, because this one lives in a weird space between legitimate academic philosophy and internet meme, and somehow it's both at the same time. Here's the thing, Nick Bostrom didn't just casually suggest we might live in a simulation. In 2003, he constructed a logical argument that's genuinely difficult to dismantle. It goes like this. If technologically advanced civilizations can eventually create detailed simulations of entire universes, and if enough of those civilizations exist across the history of reality, then the overwhelming majority of all universes in existence aren't real. They're simulations, which means statistically, you're almost certainly inside one right now. Now, before you dismiss this as sci-fi nonsense, consider what physics actually tells us about the universe at its most fundamental level. Everything reduces to information, quantum states, bits, computable processes. The universe doesn't just resemble a program, it behaves like one. Nothing in physics rules out simulation. The only question is whether a civilization capable of running it exists somewhere. And serious people take this seriously. Elon Musk estimated in 2016 that the odds we're living in base reality are roughly 1 in billions. The academic philosophy community publishes dozens of papers annually on the hypothesis. This isn't fringe, it's uncomfortable, but it's not fringe. But here's where it gets complicated. The simulation hypothesis has an absolute unfalsifiability problem. There is no experiment, no observation, no measurement that could ever definitively distinguish a perfect simulation from base reality. None. Zero. Which means you either find that deeply fascinating or you find it disqualifying. It depends entirely on whether you think something needs to be testable to be worth thinking about. And if you do take it seriously, the implications are genuinely strange. Because if simulation theory is correct, the origin of the universe isn't physics. It's code, somewhere, in another layer of reality we can't access or observe. An intelligence wrote the laws of our universe the way a programmer writes the rules of a game. Set the gravitational constant, defined the speed of light, calibrated quantum mechanics, and pressed run. The Big Bang wasn't a cosmic event, it was initialization, which is either the most disturbing idea on this entire list or the most liberating one. But either way, it makes you wonder whether that the real answer to how everything began might not involve physics at all, but rather the mind that designed it. And speaking of eliminating the need for anything before the beginning, the next theory doesn't just answer what came before the Big Bang, it makes the question itself meaningless. The no-boundary proposal. Picture the surface of the Earth. It's finite. You could measure every square mile of it. but you could walk in any direction forever and never hit an edge. No wall where the ground just stops. The surface curves back on itself, completely closed, completely self-contained. In 1983, James Hartle and Stephen Hawking proposed that the entire universe works the same way, not just in space, in time. The no-boundary proposal suggests that space-time is finite but has no boundary, no edge, and no starting point. The universe doesn't begin at some moment zero where everything suddenly switches on. Instead, as you trace time backward toward the Big Bang, time stops behaving like time. It curves smoothly into something resembling a spatial dimension, rounding off like the surface of a sphere approaching its pole. No sharp point, no first moment, and here's the most famous analogy in modern cosmology. Asking what came before the Big Bang under this model isn't a question that lacks an answer. It's a question that lacks meaning. It's like asking what's north of the North Pole. The concept simply ceases to exist. The question dissolves. That's what happens to time in the no boundary proposal. The before dissolves. The implications are staggering. If the universe has no starting point, no edge in time, then it requires no external cause, no trigger. Space-time simply exists as a closed, finite, edgeless geometry that needs nothing outside itself. Hawking himself was blunt about this. A universe with no beginning requires no creator in the traditional sense. Now the honest part. This proposal requires a complete theory of quantum gravity, which does not yet exist. Even among quantum cosmologists, it remains deeply speculative. But here's what makes it the right place to end this video. Every single theory we've covered, from the Big Bang to cosmic inflation, from oscillating universes to simulation theory, every one of them reached toward the same wall, the moment before existence. Some theories tried to climb that wall, some tried to push it further back, hiding it behind cycles or dimensions or parent universes. The no-boundary proposal erases the wall entirely. It says the wall was never real. It was an artifact of the wrong question. And that might be the most profound thing science has ever attempted. Not an answer to the oldest question in human thought, but the possibility that the question itself was never valid to begin with. If you enjoyed this video and want to see more, click the video on the screen now.